All right, today we want to finish up talking about the ambiguous case of the law of sines. This is the case where we're trying to solve a triangle, and the given information includes two sides and the angle opposite one of those sides. So SSA is different than SAS. That was from the law of cosines. That's where we had two sides and the angle included in those sides. The ambiguous case of the law of sines is when we have two sides and the angle opposite one of those sides. That's the key part that forces us to use the law of sines. We have an opposing set of information, a side and the angle opposite that side. So we had to name the three different parts because this is the ambiguous case of the law of sines, because we could end up with 0, 1, 2, or 1 triangles. So the parts will be the given angle, the side opposite the given angle, and the other given side. Last time, we talked about why this was the ambiguous case. And so visually, if we put on this horizontal, the third side, just this is where the third side is going to have to go. And I make the given angle go from where the third side is going to go up to the other given side. And then this space, we're going to have to connect the other given side to the line where the third side is going to be. That will tell us the shortest distance, the shortest length the side opposite the given angle can be. So if we calculate the height of the triangle by taking the other given side multiplied by the sine of the given angle, that will give us a minimum value for the side opposite the given angle. If the side opposite the given angle is less than the height, then we get 0 triangles, because the side opposite the given angle just kind of like dangles there. And it can't reach the third side after it's been connected to the other given side. It's going to have to connect at this point, and it just kind of hangs there. It can't reach the third side. If the side opposite the given angle is exactly equal to the height, then we will have exactly 1 right triangle. Then if the side opposite the given angle is a little bit bigger than the height, we can swing the side opposite the given angle to make 2 triangles. So that is the one that I want drawn in here, the 2 triangles. And then we can have the same length on the other side. So the first angle that we're going for, that we're going to have to go for, is the angle opposite the other given side. And so here's why we get two copies, 2 versions, because we find a reference angle and we have a quadrant 1 angle and a quadrant 2 angle. So when we're going to have 2 triangles, we have a quadrant 2 angle and a quadrant 1 angle. And then the fourth case is if the side opposite the given angle is greater than the other given side, then we're going to try to, we swing it down and meet the third side way off the page over here. But if I swing that side over the side opposite the given angle the other way to try to get this quadrant 2 angle, it just goes too far. So if I have the side opposite the given angle greater than the other given side, I can touch the third side on one side, but I can't swing it around to get that quadrant 2 angle like we did in the 2 triangle case. The best part of this whole process is that you don't have to know which case you're in. The numbers will tell you if you're going to have 0, 1, 2, or 1 triangle. The last case that we had to cover is when the side opposite the given angle is greater than the other given side. What if we don't notice that we don't have two triangles? So let's cover that. I forgot what angles I was using yesterday, so I'm just going to start afresh. Say theta is equal to 32 degrees. Let's say the other given side is going to be B, and that will be 17 meters. I want big triangles here. And I'm going to make the side opposite the given angle. It's going to be greater than the other given side, and we're going to pretend that we don't notice that yet. So A is going to be 21 meters. We've got to identify our parts. The given angle is 32 degrees. The side opposite the given angle is 21 meters. And the other given side is the 17 meters. Note that in this case, since the side opposite the given angle is greater than the other given side, if we notice that right away, we don't even bother calculating the height. We know we're going to have one triangle because the side opposite the given angle is too big to make two triangles. I'll just try to spin it the other way and it would go completely around and just give us that one triangle that we had before. All right, so let's pretend that we did not notice that the side opposite the given angle was greater than the other given side. And we're just going to jump right into the law of sines, which I hadn't even written down yet so far. So I'm going to take the sine of alpha divided by A is the sine of beta divided by B. I need to solve for beta. I'm solving for an angle. That means we're going to need an inverse trig function. Beta is going to be the sine inverse of 17 sine 32, close parentheses, divided by 21, close parentheses. And we just grab our calculating machine, or you look sine 32 up in your scientific calculating book. Oops. Sine inverse of 17 sine 32 close parentheses divided by 21 close parentheses. 25.4 degrees. Now, we know we are in the ambiguous case. So we might put that 25.4 degrees into quadrant 1 and quadrant 2, just not noticing that we are in the one triangle case. So maybe we don't notice that this is the one triangle case. And so like a character in a horror movie, we just go right through the door. Oh, I'm sure it'll be safe over here. And then we turn to our friends and say, I'll be right back, knowing that, and then the audience really knows. So let's go with a quadrant 1 and a quadrant 2. So in quadrant 1, beta is just the 25.4. And in quadrant 2, beta is 180 minus 25.4. $154.6. And like the audience in the horror movie, you can already see why this is going to be a problem. So once we have two angles, we subtract to find the third angle. So gamma is 180 minus the 32 that we were given, minus the 25.4. And so our gamma, this is a 180 minus 32 minus 25.4, 122.6. Now that I have gamma, I can use the law of sines again to find side C. So I'll just say sine of 32 divided by 21 is the sine of 122.6 divided by C. So C is going to be 21 sine 122.6 divided by sine of 32. Grab our calculating machine. 21 sine of 122.6, close parentheses, divided by the sine of 32. 33.4. We'll round to the nearest tenth for whatever reason. And those are the three parts that we needed. Beta is 25.4, gamma is 122.6, side C is 33.4. That, along with the three pieces of information, is one solved triangle. Now we go to the other side. So this is the ambiguous case of the law of sines. There's another angle that has a sine of 17 sine 32 over 21, 154.6. Once we have two angles, we subtract to find the third angle. So the first angle that we find is used as reference angle in quadrant 1 and quadrant 2. So gamma is 180 minus the 32 that we were given, minus the 154.6. And now the rest of the audience is on board. It's like, oh, now we see what you were talking about. Since this angle is coming out negative, we can't have a negative angle in our triangle. And that's when we realize, oh, this wasn't a two triangles case at all. Then we look back and see that the side opposite the given angle was greater than the other given side and say, should have checked, I would have saved myself a little bit of work. So it works out negative 6.6 degrees. And so that tells us that there is only one triangle here. So I don't have to worry about this quadrant 2 stuff because my other gamma would have to be negative. So sometimes it's helpful to figure out how many triangles you're going to be faced with, 0, 1, 2, or 1. But the numbers will let you know how many triangles they're going to be. If it's going to be 0 triangles, the first angle that you find, you're going to have a sine inverse of something more than 1. And so there is no angle that has a sine that's greater than 1. So you get that domain error and you say no triangles. And that's your favorite case because that means you're done. You don't have to do any more calculations. In the two triangles case, you find that first angle and say, I just make this is the ambiguous case. I put this as a reference angle in quadrant 1 and quadrant 2. And then I solve the quadrant 1 version, and then I solve the quadrant 2 version. If it happens to be the one triangle case, you get an angle at the beginning. You make a reference angle in quadrant 1 and quadrant 2. Quadrant 1 will solve no problem, just like normal. In quadrant 2, you end up with gamma, the third angle that you find, being negative. And that tells you it was the only one triangle case all along. The only other one triangle case is where in the sine opposite the given angle is equal to the height. And this one we can't pull off unless we have some very specific requirement. So if I just approximate things, it won't come out exactly. So I usually don't even try for that one. I just give you a right triangle. In particular, we have to do a sine inverse and come up with that first angle that we find. We have to do a sine inverse, and it has to come out to 90 degrees, because that first angle that we find is the one in this corner. And if I want the side opposite the given angle to be equal to the heights, I've got to do a sine inverse. The sine inverse has to come out to a 90-degree angle, which means 17 sine 32 has to be exactly equal to, or the other given side times the sine of the given angle has to exactly equal the side opposite the given angle. And that means using lots of decimal places or very specific angles like 30 degrees, so that the side opposite can be 1/2 of the hypotenuse. That's why even though there's 0, 1, or 2, I listed as 4 possibilities. 0 triangles, 1 right triangle, 2 triangles, or 1 triangle. Any questions? I don't know why I like solving triangles so much. I think it just because it makes so much sense. And it looks like, to me, it just looks like an extension of the right triangle trigonometry things that we did before. The law of cosines is like your generalized Pythagorean theorem. The law of sines is the generalized version of sine of theta is opposite over hypotenuse. So law of cosines is what you do with the Pythagorean theorem when you don't have a hypotenuse. Law of sines is what you do with sine of theta is opposite over hypotenuse when you don't have a hypotenuse. It's a good way to remember that sine of 90 is equal to 1 and cosine of 90 is equal to 0. A very roundabout way to remember that, but hey, whatever works. Any questions? That's why this is one of my second favorite things to do in trigonometry. Any questions, comments, deep thoughts, snide remarks, ways to get more triangles? I don't know why I like this part where you could kind of easily figure out how many triangles you're going to have to look for, but you don't have to. You can either know going in and say, I am comforted because I know I'm looking for 2 triangles. Or you're just like, oh, nah, just jump in. Woo. So it rewards both kinds of gameplay. Careful planning and executing your plan, or just kick in the door. I like both kinds of D&D groups. So any questions, comments, deep thoughts, or snide remarks? All right. I haven't put up homework assignments from solving triangles. I just noticed that I haven't done that because I say, let's take a look at how many problems you're gonna have to do. And currently that number is 0. These problems come from chapter 7. So now that I know that, I'm gonna have to jump in. I'm gonna post some problems from chapter 7. It's 7.2 and 7.1 and 7.2, law of cosines and the law of sines. All right. The next big thing is either going to be vectors or, so boring, vectors or complex numbers, which is like my favorite thing. I think it's going to have to be vectors. We'll save complex numbers for a later date because vectors is actually kind of useful. Maybe that's why I don't like it as much. I like the weird stuff, I guess. All right, so I know that was kind of short. So this class per minute was a little more expensive than the other ones, but that's going to do it for today. That's going to do it for this week. Everybody have a good weekend. I'll see y'all on Tuesday. I don't know if that's the right order. I'll see y'all on Tuesday. Everybody have a good weekend, which is the more natural order. That's going to do it for today. That's going to do it for this week. I'll see y'all on Tuesday. Everybody have a good weekend. Thanks for playing. Yeah, let's just go with that order for now.
Thank you. Have a great rest of your week.
Have a good week.